Hello and welcome to the module 5 of this course. Here we are going to introduce deep neural network. We discuss first part of this in this part A of module 5. In this lecture, we first give the introduction of the neural network. Then why this deep neural network is preferable over the shallower networks. Then we discuss the role of hidden layers. First we define hidden layers and then find out what are the role of initial and higher layer neurons for these hidden layers. And we take an example to understand this concept. Okay, we'll start the definition of the deep learning. The deep learning is defined this way, that it allows computational models that are composed of multiple processing layers to learn representations of data with multiple level of abstraction. So this definition is very important in our course. Now, what it is saying that this deep learning is basically a computational models. At the very beginning stage, we can say it's a neural nets. And why it is a deep coming? A neural nets with multiple hidden layer between input and output layer. So what they are said, that are composed of multiple processing layers. These processing layers is basically hidden layers. And what these hidden layers are doing? They learn representation of data with multiple level of abstraction. What does this mean? Now there is an image as a data, input data, and its pixels are given as input. Now this image is represented in a different hierarchical fashion. That my very initial, very primitive description of the image is basically some primitive geometrical patterns like lines, centered lines, small square and something like that. And then we go for some more complex patterns like planes and hyperplanes kind of things to represent. When these more layers, that means layers later with little layers, we're going to represent this image with more and more complex, and in final layers basically a kind of very close to the objects of the images. So what is important here, that we are going to understand or represent a data with a different level of representation of a different complexity. That is the meaning of different level of abstraction. So this is a very, very important for in our course, and this is basically defined by these three stalwarts of today's deep learning world, and LeCun, Shubhendu and Hinton. Now we are going to understand the meaning of this definition in the entire course. Okay, so with this background, we try to understand why deep learning is so successful today. Okay. Now the three things is very important to understand. We are put it in a very simplistic manner. First thing is data. Data means by which we are training our models. Now here you can see a plot. The x-axis is amount of data, y-axis is prediction accuracy. And you can see here, after a certain amount of data, definitely it is not very big data, small data, this Salver model and deep learning models are performing almost similar. But when amount of data is increasing, then slowly the performance of the deep learning outperforms the Salver nets. So if we have lot of data in supervised paradigm, this data should be annotated. Maybe it's costly, but still. Then our deep learning models performs much well, substantially well than the Salver. So the one major aspect is availability of the training data. Another thing, since lot of data are involved here and a lot of computation, because it is a layer by layer structure, and in deep networks it's a huge number of layers in between, hidden layers in between layer. So it required a huge computing power. Okay, but thanks to some modern day IT companies or hardware companies like Nvidia, Intel, they are producing very powerful GPUs which make or this computing power available to us. And third, and most importantly, that the efficient training algorithm, because that we're going to see in this lecture very in detail, that what are the normal backpropagation algorithms may not be very good solution or training algorithm for the deeper structure. That we're going to understand that what is the problem and how this problem is managed. So when these three are available, slowly, I think around from the 2010 onwards, slowly these deep learning models become prominent over the Salver models, and now everything is deep. Now, what is the basic difference of deep learning and a conventional machine learning? Now here you say this is the conventional machine learning. Fine. This is the data. Let's say it's the image. Now we extract feature. Most of the cases this feature extraction is manual feature extraction. It's called feature engineering. Okay. So these are the geometrical features, statistical features, some patch kind of features, whatever. This feature is extracted by a human. And when we get this feature is subjected to our machine learning models. That may be regression model, classification model, maybe different kind of, it may be a neural net, it may be support vector machine, and anything. And this is going to infer the output. So we predict like this. So this is the main three steps: feature extraction, network, this model network, and predictions. But in deep learning, these three things are clubbed in a single network. You can say the input layer, and this input are directly fed to the network. So the feature extraction and classification and predictions all are done by this network. Okay. That we have to understand, that how a network is going to do all three things. Feature extraction, you can say automatic feature extraction. There is no manual intervention is there. Then classification and giving the output as a prediction. So very simplistically, is a kind of oversimplified way to say that the initial layers of the deep network are basically involved for this feature extraction, and the later layers is doing the classification or prediction task. So that is the major difference here. Okay. What is the challenge? That we have to understand. Now we have to build a network. How we have to build a network? This, in one side, it is a acts as a automatic feature extraction, and another side classification and output generation or inference, producing the outputs. Now the question is, why the deeper architecture are preferable, or it outperforms the shallower nets? So very in simple sense and simplistically, the deep neural network is basically a conventional neural network with more number of hidden layers. Okay. So as we have discussed, the initial layers is basically do the automatic feature extraction, and the later layers are basically doing the prediction. Okay. But the main issue is here, why many hidden layers are important, or how the deeper structure helps to make the model more perfect. Let us find this question, answer of this question. So as we have understood that deep learning means is a neural network with several layers of nodes and between input and output, and this series of layers are doing the feature identification and processing in a series of stages. Okay, that is very important. So these things, this feature identification processing in a series of stages, just our brain seems to do. So as we have discussed, initial layer are basically doing this automatic feature extraction, and the later layers are basically doing the classification or inferencing. But the very interesting question is that this concept is not new. People know this concept from very early ages, like it was found almost 25 years back when multilayer perceptron was invented. But then what actually happened now? What is new? The problem is actually that, a problem actually was that the algorithm to train this multi-layer perceptron, where the hidden layers is 1 or 2, maximum 3. These algorithms, for example, backpropagation, etc., is not very suitable for deeper layers. There are 10 layers, 15 layers, 20 layers. It performed very poorly. The main issue is, or we can say one of the main issues is vanishing gradients, as we have discussed before, that if we keep on differentiating the error gradient from output to input layer by chain rule kind of, then the error gradient is decaying towards the initial layers, and since it is getting low and low, so the weight updation specifically in initial layers is not that much fruitful. So it making the convergence very slow, or sometimes it stop converging. So the algorithm is not working for deeper layers, and that is the new. This is the main advancement or improvement deep learning in recent times. So the very new algorithms, training algorithms have been developed that successfully train this deeper structure or many layers neural networks. And that is we are going to understand how. What is the algorithm? In a very simplistic way, very naive way, but we try to understand this. Okay. So, okay, now first of all, we have to understand what you mean by hidden layers. What actually it do, and why it is more and more the hidden layers in general increase the expressive power or making the model more accurate. So we know that for deeper structure, hidden layers between input output in general high than their salad structure. Now these hidden layers are intermediate computational layers. Okay, and that also we have discussed that it transforms the input data into increasingly abstract and hierarchical features. That for image, the initial layer model the edges, maybe the deeper layers identifying the complex structure like objects, and so on. Maybe for a text, the initial layer is basically do the letter level or word level embedding, models word level or letter level embedding, and slowly we go sentence level, paragraph level, and so on. Okay, so this hidden layer enables our models to learn complex and non-linear patterns. That is very important, beyond a simple input-output mapping. If we try to understand or visualize this just for a classification problem, if the decision boundary, if you see there is a deeper structure, the decision boundary, complexity of the decision boundary, it's not a now straight line. In a two-dimensional case, it is a complicated, very high order polynomial curve. So it has a more expressive power. Okay. So that is we are trying to say. Okay. In general, hidden layers is a black box. We don't know what is the output of the hidden layer in general. So it extracts the relevant features and allow network to solve the sophisticated problem. Sophisticated means most complex problem, and image recognition, NLP problems, kind of thing. Try to understand the context, sentence, kind of complex problem. So that's why the hidden layers or more hidden layers in general, I said in general because we'll see later, it's not necessarily true that how many hidden layers, more the layers, more the accurate, is not always true. But that I don't want to comment on this because of understanding. We'll see later. Okay. Now we try to understand in bit depth what hidden layer actually do. As I said, that this feature extraction kind of thing is done by this initial hidden layer, and when it is the hidden layers from input to the output, increasing level of complexity of representation or increasing level of complex representation, so in a different level of abstraction. Okay, so more and more we go to the input to output, more abstract understanding, more abstract representation of the data we can model. So as we give the example that for image recognition, first layer might find edges, next combines edges to shapes, and deeper layers are parts of object. Okay, so this is this hierarchical feature extraction that is basically hidden layer 2. Then it imposes non-linearity. That is very, very important, because this activation function like ReLU, sigmoids, hidden layers introduce the non-linearity. Now actually what non-linearity is doing, if you try to visualize, that we have decision surface or decision space, it helps to bend the decision space, create more curves in decision space in new ways. Since if you think in a kind of supervised way, that these bends are actually driven by the data and the corresponding levels, so that it learns properly. What kind of bending is necessary, it learns it. So mode layers allow more bends, which helps them make more complex decisions. And definitely, for a very simplistic understanding, this complex decision boundary fits the training data well. And if we use our we can keep vigilant regarding this overfitting concept, then also it should be a very good for testing it also. Okay, so in general, network with higher number of hidden layers has a more expressive power. The third point is the data transformation. So the inputs are given, for example, in this image example, inputs are given as a means of pixels. Then it's transform the pixel into edges, then edges to the shapes, shapes to the kind of objects. So they transform the input to a new representation, and that makes it easier for the final layers. That means we are going to take the decision of the or inference decision to make the accurate prediction. Okay. So that actually the idea of hidden layers. That we'll take an example and understand that how these things what we are claiming here, how hidden layer is do. Now the question is, why these layers The intermediate layers are called hidden. So it is primarily because that these layers is not directly exposed to the external input or final output. In that sense, very simplistically, it's kind of intermediate processing layers. So it is basically that the internal computation are being done by these layers. And what kind of computation? What we said, that after taking the inputs, they try to model the inputs in different layers of representation or different layers of abstraction, from simple abstraction to the higher abstraction, from input to the output direction. So the initial layer model the primitive structures are, for image example, it's just edges, shapes like, and more deeper or later layers models the object or object kind of shapes, so that it basically helps for the final layers to infer more accurately. Now also with that we have discussed that neurons in hidden layer receive input, multiply them to the weights and add a bias, and then pass result to a very activation function. That is the very basic things is done. That is important. They are basically kind of a neuron of activation there. They are doing this. And another important thing, that output of one hidden layer become the input to the next or successive hidden layer, creating a chain of transformation. Now that is also very important. Okay, so with this understanding of hidden layers, and our neural networks has many new hidden layers, or we can say our deeper structure has many hidden layers. We are trying to understand that how we are going to represent the input in a different layers or different level of abstraction. Now here you can see this is a car image, the vintage car image, vintage car. Now if we try to understand how this image is being represented, so most simplistically you can say represented by a matrix of pixels. Now these pixels are given to the network. Now here this is the low level features that is being modeled by the very initial layers of neurons, and you can see that there is some sort of primitive structure or primitive geometrical patterns, like the horizontal line is a slanted line, okay, something like this in a different direction. So this is a very less complex patterns that you can say the very primitive pattern. That's all. Now then these inputs are going to the low level features or these layers to the mid level layers. So in general the mid level features extraction, if you see here, you can see that it is not exactly same, but some kind of object or shape of object is coming. You can say a part of shapes or something. that maybe it's a steering wheel, or it's a kind of tire, and so on. So mid-level features is basically this kind of, if you just try to visualize. Now see what is the high level features. Here the tires are more prominent. Even a human can understand this. Okay, oh, maybe a part of tires, or it's a steering wheel. Okay, this is the looking glass kind of, and so on. So what that we have to understand, please try to recall the definition of the deep learning. Deep learning is basically a network of a series of layers, and these layers, these hidden layers, is basically represent the inputs in a different level of abstraction. Exactly, it is happening here, and this is the main strength of the deep learning over the solver model. Some similar example here is a face recognition task. So these are the pixels, image pixels. Now here it is the edges, you can see. This is the first initial layers. And now next mid-level features is some part of the objects. Some part of eyes, some part of mouth, part of nose, eyebrows, and something like that. So that is very important, that from this very kind of primitive structure, we are getting something which are more prominent or more close to the actual object. And when we go to the final kind of layers, are very close to the final layers, you see, it's almost face-like objects. And if we can get, it is very easy for your classification layers or inference, who is taking the inference, to find out or to decide this particular face detection in a very accurate manner. So these are the very important understanding, that the hidden layers is going to model the inputs in different layer of abstraction, so that our final layers is going to predict or take the inference or give the inference in a very accurate way. So in this lecture we discussed about deep neural network. What is the basic understanding of this? Then why deep networks are preferable over conventional machine learning models? Then we introduce hidden layers, and we try to understand role of initial and higher layer neurons. Why? Then we give an example, and by this example understand this role of initial and higher layer neurons. In this next part, we continue this discussion, this introduction to the deep learning network, deep neural network, part 2. Thank you very much.